Right, we come to the last part, which is star death. We've gone through, you watched the video on how a star is born. It's born in a gas cloud called a nebula. This large gas cloud gives you many stars, and all large stars. Small gas clouds give you few stars and only a few medium-sized stars. Our star was also formed in a massive gas cloud with all manner of other stars. Our star was not just born by itself. Okay, we were all in a gas cloud together. It's just that we have drifted apart after we have been formed in the last 5 billion years. Our sun has drifted away from its siblings, okay, as a single star. As we know, many stars are part of binary and tertiary and quaternary systems. Ours is a single star. That gives us a more stable orbit and probably is one of the reasons why life has been able to evolve on this planet. It doesn't mean that binary systems and tertiary systems do not have the ability to harbour life. We've discovered millions of planets out there. So we know that planets are nearly just a byproduct of star evolution. And right at the beginning of the Big Bang, the first stars are made purely out of hydrogen. But now we have what we call second generation stars. Our star is a second generation star. So it formed after another star has exploded, another supernova. So a star has exploded, a massive star has exploded, seeding space with all of its gas, hydrogen, helium, and the heavier elements, and then it's condensed to form our solar system. And that's the reason why we have planets which have rocky cores of iron and so on. And iron is going to be the big bad wolf in all of this. It's going to be the cause of the death of everything. So let's have a look at star death and why star death occurs and what's the different ways. Now, yesterday we had a look at the different evolutionary tracks. So let's have a look at the different evolutionary tracks here. That's just a general main sequence star, and this is the first question on the book on page 41. And it says, on the HR diagram, plot the evolution of a star whose solar mass is very small. Okay, and the solar mass that it's telling us is 0.1 solar masses. Okay, so 1/10 the size of our sun. 1/10 the size of our sun would probably be quite a large red dwarf. So we're down here. So these stars down here are the stars that we're looking at, that we're going to be looking at. And these stars are red dwarfs. And I'm not going to go into the debate whether dwarf should be dwarves VES or dwarf FS. I'm just going to go FS. It's like wives and wives. Okay, rightio. Now, what does a red dwarf's life go like? Well, red dwarfs that were formed at the beginning of time, after just after the Big Bang, after everything cooled, those ones are very, very small stars. They will be burning now probably until the end of the universe. Remember, it's the big blue stars up here that, they're big, they're bright, they party hard and die young, basically. Okay? These ones over here are the conservative, small little, they're the accountants of the universe. Okay? Sorry, I've got friends who are accountants, but they'd kill me if I heard that. So they just sit there and they're quite dull. They just hydrogen into helium, hydrogen into helium, hydrogen into helium. And they will do that for billions of billions, hundreds of billions of years. Considering that the universe is only 13.8 billion years old, they've been doing that for a very long time, and they will still keep on going. So there are stars that are born now, or have been born, which won't die before the end of the universe dies. So they are so long. So these are hundreds of billions of years. But what happens if they do die? Well, nothing much. They go out as boring as they live their life. Okay? So what do they do? So just going forward, and there's the stars we're talking about here. So we'll just choose one good old little fella there. Okay? We have to make sure that they are on ZAM. What does ZAM stand for? Z-A-M. Zero age main sequence. Good. And then as they age, they will migrate to the other end of the thickness of the main sequence band, which is terminal age main sequence, TAM. So we go from ZAM to TAM. Okay, ZAMs to TAMs. Okay, and we have, sorry, I won't do the Tin Tam joke, it's embarrassing. Okay. Now, no, it's Zim Zam Tin Tam, sorry, just a second. Okay, rightio. It's terrible. Okay, it's a dad joke. Okay, now, after it gets to terminal age main sequence, it's not going to be able, it's not fusing hydrogen to helium. Remember, while you're on the main sequence, hydrogen is fused into helium. That's the whole point of the main sequence. Main sequence stars all fuse hydrogen into helium. And then simply what's going to happen is it will swell up a bit because it's going to run out of hydrogen in the core. Now, can I just make just before we go any further, I want to make sure that you are very clear. When I say a star runs out of hydrogen, there is our star. This is just any star. This is the core. Okay? Most of the star is still made up of hydrogen. There is hydrogen out here in abundance. Okay? But it's only the hydrogen in the core that can fuse. It's only the hydrogen in here that has the ability to overcome the hydrostatic Coulomb barrier. That's the proton-proton push away from each other. That they are close enough together, that's dense enough, and they are moving so rapidly that they can fuse together in a reaction. The hydrogen out here is just basically bystanding. It can't do anything. It's not hot enough to fuse. So when we say we run out of hydrogen, we're running out of hydrogen only here in the centre. Okay? Is there ability to get some hydrogen from the out here to go into the centre? Yes, we can, but only in larger stars can we push that in there. Okay? And that will become what we call helium flash later on. But we're talking about hydrogen in the core is running out. Now to fuse, the other option that now has, apart from hydrogen, is to fuse helium. To fuse helium, you need a lot of heat. You need more heat. The problem is there is not enough gravitational pressure in a red dwarf to push it in. So we can't fuse helium. So it tries to, it might have a small amount of helium fusion, but not much. It might just slightly grow in its size for a bit, and then what will happen is it will just turn off, collapse in brightness, and then simply cool down. It won't collapse any more in, okay? It's not a really massive star that will collapse into a white dwarf. So these just become black dwarfs. The first thing they become is a brown dwarf. Brown means, as you remember, if you were to...
Could any members of the choir?
Okay, so after it's, the fusion stops in the core, no fusion happens, the star doesn't really shrink too much, it just simply is like Jupiter. Jupiter is just like a big ball of gas, it doesn't glow anymore, so it starts to cool down. Okay? As it starts to cool down, it will lose its red tint. It then becomes, the next colour down is that reddy brick tint, and then we call it, it's still hot, but it's just radiating. It's like when you turn off one of the heaters of your, cookers of your range. It starts, as it cools down, it goes from red to that brown, and then eventually it's off. It's still got some heat coming out off it, but you can't see any light. So the infrared comes out. And it becomes a brown dwarf, and then what we call a black dwarf. Okay, a black dwarf, there probably aren't any black dwarfs in the universe yet, because remember, these things are still going. Okay, so a black dwarf is just a nice cooling down, and as it goes down, it will just simply go off it becomes dimmer and dimmer and dimmer and dimmer, and out it goes. Okay? Rightio. So the evolutionary track is quite boring. It's just really in that corner. Okay? And there's a variety of other possibilities. We start over here, it might go like that. Down here, okay? It's not big enough to shrink, to grow into a red dwarf and then suddenly collapse down into a white dwarf. Okay, a red giant. Did I say red dwarf before? Right, yeah. Okay, so that's the evolutionary track for a dwarf star. Now let's have a look at the evolutionary track for our star. Okay, so we're talking this time as a comparable to 1. So we're comparable to our size. So here is us in the centre here. We're talking about these stars in the centre. So we've divided our evolutionary amount into 3 different categories. What happens to the red ones, what happens to the middle ones, and what happens to the big bright blue ones, which are more exciting. Okay. So let's just take a star like our sun. And as we saw yesterday, when a star is born, it begins up on the 0 age main sequence, and it then migrates as it ages towards the other end. Okay? So our sun is it's changing, its brightness and its size and its temperature as it ages. The way that it goes across, it could start down here and go across to there, could be up here and go up there. They all have different pathways, and depending on where you are, how more steeply that crossing is. So we're just going to take a general crossing there, right in the middle. So that's Zam and Tam. Zams and Tams. Don't forget the S. The S stands for sequence. After it gets to this here, so this is, at this point here, always hydrogen is fusing into helium. After it goes here, it then grows and expands over the next billion years. Okay, this is not a very fast event. It's quite slow. It's a billion years in time. But it's about, if this is 90% of its stage, if this is 90%, this is about 9% or 9.9% of its time. Okay? Now notice what happens as it grows. It becomes brighter because it goes further this way, so it's brighter. And it also goes sideways, so it becomes redder. So these, it grows, become brighter and redder, and this is the reason why we call it a red giant. Okay. At this point, what is it doing? It's doing a whole variety of things. It's firstly fusing helium into carbon by the triple alpha. Now the triple alpha is helium plus helium plus helium. So it's 3 heliums becoming carbon. That means that now carbon is starting to go into the centre. Now let's have a look at what's happening. In the core of that star, so I'll just do a better diagram. So let's get a star here. And here's our core. There is hydrogen out here. There is hydrogen in the centre, which is fusing. Now, once hydrogen is fused, it gets into a waste product called helium. So helium is formed. Now, helium has four particles rather than just one particle, so it's heavier. And under its own gravitational, it makes its way into the centre of the core. So we get a core made up of helium. This core grows and grows and grows and grows and grows and grows until it gets up to be most of the core. Not entirely all the core. There's still enough hydrogen out here which is starting to fuse, but most of the core is made of helium. What happens then is under the pressure of the star, the pressure from the outside of the star pushes the core in, and the core starts to shrink in on itself. As the core shrinks in on itself, there is enough pressure inside the core to fuse helium into carbon. And then suddenly carbon starts to form in the centre. But this process is rapid. This is very, very it's huge. It's got a very fast process, whereas the proton-proton and the carbon-nitrogen-oxygen cycle is quite a regulated speed. This is quite fast. And therefore, a lot of energy is suddenly radiated out of the core. What that does is that sudden output of energy makes the star hotter plus larger. Okay? Why does it make it larger? It pushes it out. It makes it swell. So what is swelling is not the core. What is swelling is the out part of this outer zone. And as from last year, we know this is the convection zone and the radiation zone. So this becomes quite larger. And it grows to quite a significant amount. But the star is also hotter. Therefore, it's brighter. It's hotter and it's giving out more light. So it becomes a bigger star which is putting out more light. Brighter, bigger. Now, even though it becomes brighter, the actual surface area of this is much larger. Spheres have massive surface areas. So even though it is much brighter, the amount of energy being lost per metre squared, this is the more important thing. So energy per metre squared drops. Even though it's putting out a lot more energy, because there's much more surface area, the energy per metre square drops. And we perceive that as a colour shift. We see this from going from a yellow colour and now it looks red. Even though the sun, that star, is much hotter. It's much brighter. There is more surface area for all this energy to be lost through. Okay? Right, so that's how it swells to become a red giant. So it's a hotter, larger and redder star. The core is the most important thing. This is what's happening. Now it's swollen up, it's still, this star is no larger than it started out to be. More massive. It's the same mass star. It's just less dense. Does that make sense? It's a less dense star. So it's gone from being a class 5 star, which is the main sequence, into a class 2 star. And maybe even a class 2 or class 3 star. Okay. Okay, please remember it's the core of the star which is the important part. So in the core now is starting to accumulate what element? Carbon. So let's have a look at the core alone. So I'm just going to rub out the centre part. Oops, rubbing out the centre part. Come on, catch up with me. Okay. So here is the core. Okay. There is now an increasingly large core of carbon starting up. So this is where we're starting to accumulate carbon. Okay? That's all carbon formed from them. So hydrogen is going out into helium here, helium into carbon going on here. So carbon starts to accumulate in the centre. Now, can we fuse carbon into a higher thing? Yes, we can. Okay, but it takes a lot of energy. So carbon can fuse into nitrogen and carbon can fuse into oxygen as well. Okay, by different processes. Okay. Now, that requires a lot more pressure and a lot more heat. So eventually, the amount of carbon in the core and a little bit of nitrogen, a little bit of oxygen starts to accumulate in such a way that nothing else can happen. There's not enough energy to fuse any more carbon into oxygen or carbon into nitrogen. If there's no more energy, because it requires a lot of energy for this to happen, a lot of pressure, what will happen? This will start to stop, and therefore the actual star will start to collapse. Now, what happens is that the core starts to collapse in. As the core starts to collapse back in, it starts to put more pressure on the helium and the carbon that's already in there. And so once again, it starts to reignite. So we have a process for a long period of time where the core stops fusing and then the star's core starts to collapse, and then we start. So it goes stop and then start fusing, stop and start, stop and start. Now it's not a full stop, it's not a full start. It's a lowering and increasing. So this core starts to shrink, grow, but not much. What happens is, it takes millions of years for this to happen, to get out to here, is that we see the star start to increase in brightness and decrease in brightness, increase in brightness and decrease in brightness. Also what happens is the star starts to, as it decreases in brightness, as the star starts to decrease in brightness, here's our star again, here's our core. Now look, our core is starting to waver backwards and forwards. We see this as some variation in brightness, but what happens is the outside layers, the star starts to drop, shrink a bit, and then grow a bit. Shrink and grow, shrink and grow. As it does this, it puffs off the outer layer. Oops, that's the wrong one. It puffs off the outer layer into space. This puffing off of the outer layers, this outer layer is called a planetary nebula. And a planetary nebula is just simply the outer layers of a red giant, which has just been puffed off into space as the star shrinks and grows. Okay, and eventually, it's quite a pretty sight. I'll get you a picture up. Just hold a second. Okay, these are some pictures of some planetary nebula, and what you see here as different colours of gas, what you are seeing is hot and medium and cool. So the blue is much hotter than the red part and the yellow part and so on. And it gets beautiful different colours, they're rainbow colours. We even get some stark greens, which is the first time we ever see greens, but that's because of glowing of different elements. So these are being puffed out into space. Okay? And we can see the star, this one here especially, we can see its central star, and as it's starting to die. So what's going to happen very soon now is this star is just going to, that process in the centre of its core, which is going to make it start and stop the core, is eventually going to run out. There's just no more stuff that it can do. After it does that, what's going to happen? If there is, go back to here, there is no more hydrogen to helium, there's no more helium into carbon, there's no more carbon going to oxygen or nitrogen, there's nothing else, no more compressing of the core can make it fuse anything else. Fusion eventually will stop. There is no more outer pressure. There is no more pressure pushing this star out in all directions. So what happens to the star? It collapses. But the collapse is not explosive. It's just a collapse, a gravitational collapse. Squeezing the star closer and closer and closer together. In. As it squeezes it in, it becomes much hotter because with all that mass is now much more dense, so it becomes a very dense star. There is no fusion, and as it becomes hotter, it becomes whiter. There is no fusion, so it's not going to be pushed out again. This describes what name of the star? A white dwarf. Okay, so that's our process. So what's its evolutionary track? Its evolutionary track would be so we're going back to here. Oh, actually, back. Okay. I'll run out all this stuff. So far, we've got that we've come to swell to be a large red giant here. Now, it will eventually just go backwards and forwards a few times, getting larger and smaller, and then it will collapse in on itself as it has no more pressure in the core and end up as a white dwarf. Okay, so going through the process again, it starts off as a ZAM, goes to TAM. It then swells to be a red giant. The red giant goes through that planetary nebula stage as the core starts to burn other fuels, sometimes stop, sometimes start. This restarting is called helium flash. As the core inside the star shrinks and starts to reignite more helium burning, when we say helium burning, helium fusion into carbon. And so therefore, once again, the star has a little bit of more life. It's like getting a patient who's suddenly got into cardiac arrest and given a bit of a zap. The heart starts again, then the heart stops again. Give another zap. Every time the cardiac arrest happens, the outside of the star wafts away a little bit more, and this whole gas layer starts to go out and prettier. And then suddenly, after a while, it all goes there. And we know from yesterday's lesson how quick this process is. That process from there, the collapse down there, is only a couple of million years. Okay? So it's 99.9% of its life is in this stage, and about 1.1% of its life in the last stage. Are we okay with what happens to God? No exciting death. It's just get fat and then die. Okay? Just like most of this. That's what I'm doing. Okay. Right. Yeah. Okay. Let's go to the party. The next one are these are the party animals. These are the rock stars and the
Rose McAllister, Jenna McGregor.
Okay, these are the rock stars of the world. We know that they don't last too long. Okay. Once again, so these are approximately 10 times the size of our sun, up to even much bigger. Okay, so it's conservative. So it's the top ones. These are the blue, the upper whites, so the A zeros maybe, all the way up to the O stars. These will most likely end up in a supernova. So once again, we start our life as a ZAM, and we become a TAM, same thing as always. Then, now remember, we are already a bright blue star. We are already as bright as we really can be. The only thing that will happen is, as we get larger, we will become slightly more yellowy or reddy colour. That's it. So as we leave here, we'll move over to this point here. We can go all the way across, but no, we can go over here as well, but let's just be considered. Okay, so once again, the majority of its life is on the main sequence. This last bit is going to be extraordinarily quick. Okay, now what makes this process different than the others? Firstly, we have a CNO cycle going on in the centre of that star. That CNO cycle creates a massive rush of hydrogen into helium. If it wasn't for that CNO cycle, we wouldn't be able to sustain the size of this star. This star has been born in a massive nebula. It is massive. So, just let me go forward one and up through to there. The difference between this star and other stars is that inside its core, it starts to form shells. Now this is the core of the star. So the core gets lots of concentric circles going on in it. So this is the core. Can I put out that it's the core? So the actual star is out here, okay? This is the core only. You are only seeing what's in the centre, where the nuclear fusion happens. Okay? The core is only a small part of the massive star. So if this is there, I'm drawing that. That is that. Okay? Inside this star, oh, by the way, what's out here? Hydrogen. Masses of hydrogen, which are not ever going to be ever used. Eventually, that stuff is going to collapse down and become other suns and stars, isn't it? Now, that's the reason why more stars can be born after the death of this one. Okay, right. In the core, it originally has every part of it fusing hydrogen into helium. So this is all hydrogen into helium stuff. What then happens is what helium once again accumulates at the centre. So there is helium. Okay? Helium starts to grow and grow and grow and grow. And what happens? Because it's a massive star, the core then collapses in on itself, and then the centre of the stuff in the core here can now start to fuse. What's going to be starting to fuse now? Carbon. So I'll just undo that one. So in the centre of it now is carbon getting fused. That can grow and grow and grow. At the same time, the helium stuff is growing and growing, because remember, there is enough energy in this star to fuse hydrogen to helium, helium into carbon. Now, what can be fused in the centre of this? The next thing is carbon can be fused into neon, oxygen and silicon. So we have other stuff going on. So in the centre here is a whole mix of other things, carbon going into nitrogen, carbon going into oxygen, the nitrogen can go into neon, and so on. So these are three more shells, which are those three just there. Okay. At the same time, what is happening? The helium is starting to get bigger, so is the carbon starting to get bigger. And we now have another shell out here. Okay. Now, during all of this time, what has happened to the energy output of the star? Well, the first thing that happened is that if the star started to have, was hydrogen into helium is the biggest output of energy. So the energy output here is lower. But these reactions are faster. So it has made the star swell out just like a red giant does in the other type. What is also happening is the core is starting to shrink more and more and more and more, because as the core shrinks, it's able to have more pressure on the centre and cause these other fusions. So we have a gamut of, when I say gamut, a whole range of what do you call it, elements fusing at the same time. Then suddenly, The last thing that can happen is that iron gets formed in the centre. Iron. Silicon, two silicon atoms fuse together and form iron. Iron starts getting formed. Iron grows and grows and grows and grows and grows and grows until it gets to be quite a large part of the core. Helium has now gone to be the biggest part of the shell. Carbon has swollen out here. We are finding that we are running out of anything we can fuse. The rapid hydrogen into helium has gone. Helium into carbon, we can't do that anymore. We've used all that up. And finally, we are left with iron. Now, in the preliminary year, do we remember this graph? It's the binding energy curve. What is the king of the curve? What element is right at the top?
Iron.
Iron. Iron requires energy to be put into it to become anything else. All elements try to fuse themselves to be more like iron. Iron is the most stable of elements. Radiation, which is this end, tries to lose itself to become iron. Fusion goes this way to become iron. Once iron is formed, iron cannot be done anything with. Iron is the death of the star. Iron cannot do anything. So what happens? There is a sudden nothing going on. Iron cannot fuse, so fusion suddenly stops. What happens now is catastrophic. Here now is the full star. That's massive. Here is the core. In the centre is the iron ball that has happened. Okay? The core, the weight of this part here, oh, that's very in the wrong place. Let's move that across. I think that was in the centre. It should go there. Oops, wrong colour. Too like a nipple. Okay. Now you can only see one thing. Okay, whatever. It's on YouTube. Okay. So what's happening now is this core, the amount of pressure on the core is immense. The core is no longer pushing out. The core is going to be pressed in. The core collapses. Now, that core collapse happens dramatically fast. Okay? There is no more fusion going out. The core just collapses in on itself. So just the core is collapsing in, just this part here. Okay? Not the whole star. The whole star doesn't collapse. Okay? Now, as this goes in, it creates a hole within itself because this becomes massively super dense. Okay? What happens is the star then starts to shrink in on top of itself, but not for long. Okay? It's more the core is the thing. Now, as it becomes super compressed, iron gets fused into every other element, as well as there's some hydrogen, there is still some helium, still some silicon, carbon, oxygen, nitrogen, and neon. All of these massive things fuse. Why can iron fuse? Because there is energy now being put in to fuse iron. These fuse to now produce nickel, gold, silver, all the uranium, every other heavy element higher than iron is now produced. The core is pressed in until it can no longer think. Now it's like your hands coming together for a clap. They come in, eventually they have to rebound out. All of the core comes in, hits the centre, and has to then suddenly come back out. Like a clap, the whole core collapses in and then rebounds out in all directions. blowing itself apart, creating a really, really dense bit right in the middle, and that little dense bit right in the middle could be a neutron star or a black hole. What it does, it do the rest of the star as this core rebounds out. It blows the star apart. Remember, most of the star is still unfused hydrogen. That unfused hydrogen seeds out into space as a massive explosion, which we see as the brightest single event in the universe, a supernova. Leaving behind inside it either a neutron star or a black hole. Which one will it be? Well, a neutron star is approximately for a 10, but a black hole, if you had a massive star, more than that, you'd probably get a black hole. So we saw yesterday that if we used a 21, it would do that. Okay? So what does the evolutionary track look like for this? Finally, for our final thing. It goes through a process now of wafting off its outer layers as the core shrinks a bit and fuses other things. We know what does that cause? It causes the star. Variability, doesn't it? So this is where we get Cepheiding and so on. Our Lyrae stars, the Mira stars, all of those come from this process. Eventually what's going to happen is the star will get to a point of iron being formed in the core, and then massive collapse to a neutron star. Okay? Now, the neutron star doesn't actually appear. So can I undo that one there? Yeah. This goes off, and it's off the Hertzsprung-Russell diagram as a neutron star. If it's so large, then it goes off. Then remember, when you're in the HSC, you only have to draw this part going off to you. You put an arrow saying to neutron star. Or, what's the other option?
Black hole.
Black hole. And the last thing I want to say is, why is a neutron star a neutron star? The neutron star is made up of purely neutrons. Every part of it is a neutron. So where do all the protons go and where do the electrons go? Well, in every atom, there were protons and neutrons. Okay, we'll make the neutrons red with the black in it. And here are the electrons. But the electrons have been pushed and fused in with the protons. Now, when a proton and electron fuse together, they become a neutron. Because they cancel out.
Can you please come to student services?
They cancel out each other. Okay? So because of that massive last moment of the explosion and the compression, all the electrons that were in the star have fused with all the protons in the star, leaving only neutrons in the centre of that star. Okay?
Ali Golan, can you?
If the star, the centre of the star, has a mass so that this equation is that V becomes C, the speed of light. So C becomes Gm on R. So the radius of the final star is that, and the mass is that. So if we left over that becomes C, the speed of light, then the escape velocity of the neutron star that is left over is such that the escape velocity would have to be light, travelling faster than the speed of light. So light cannot escape this star. If light cannot escape the star, nothing can escape the star. And in this case, we call it a black hole. So a black hole is not very special, It's just a massive leftover body in such a way that this formula generates an escape velocity. Remember, this is the escape velocity of the speed of light, or greater. Okay? So they're not really big boogeymans. It's just that you can't see them now because nothing comes out. Okay, rightio, there ended the star death.